So it's a great pleasure to have Laura Havener visiting us from far, far away, Yale University. Laura got her PhD at Columbia and came to Yale as a postdoc and has been at Yale ever since, where she's now an associate research scientist. She started off working on Atlas, is now working on Elise, has been convener of a number of working groups on Atlas and Elise, and has won teaching awards at Columbia, if I remember correctly, and is also on the postdoctoral advisory committee here at Yale. And Laura's going to talk to us about her work here at Yale, exploring QCD. So, Laura.
So thank you so much for the introduction, and thank you so much for having me here today. I've had a wonderful day so far, meeting with various people in the department, and in general, just I've had an amazing 4 years experience here at Yale. And so, I'm excited to talk to you all today about exploring QCD with quarks, gluons, and the Quark-Gluon. So the physics that I'm interested in is studying the physics of the strong nuclear force. So this is the force that binds together almost all of the visible matter in the universe. And so the quantum quarterback dynamics, or QCD, is the theory that describes the strong nuclear force between quarks, medium by gluons, and all of its complexity. And so in this theory, the fundamental particles are quarks and gluons, collectively called partons, and they carry a color charge. And so in the same way that an electron carries an electric charge, the quarks and gluons have a color charge. And so in a simple picture, we have three quarks binded together inside of a proton, but this picture actually gets more complex, and I'll return to this complexity at the end of my talk. But for now, I'd like to talk about some fundamental properties of QCD that make QCD interesting and also complex to study. And so we can write out simply the strong nuclear potential as a function between two quarks, as a function of the radius between the quarks. And then we can look at different limits of the equation. So if we focus at large distances, this potential is growing with large distances. And so if you think of trying to pull two quarks apart, the energy just grows, and it becomes more energetically favorable for a quark-antiquark pair to pop out of the vacuum than to break them apart. So we have quarks and gluons confined inside of hadrons. But then if you look back at the equation and we think about going to short distances or high energy, the potential becomes Coulomb-like. And so here we get a 1/r. And so in this limit, the quarks and gluons appear as if they're free or asymptotically free. So we get a deconfined state of partons at short distances or high energy. But this picture gets even more complicated because in the deconfined region, we have the coupling constant, and this coupling constant runs with the energy. So if you go to very high energy, it gets small, and then this becomes calculable in perturbation theory, or this is perturbative QCD. If you go to lower energies, it starts to blow up, and then it becomes not anechoical, and this is non-perturbative QCD. And so we have these two regimes of QCD, confinement and deconfinement. And so how do we access this deconfined state when our ordinary matter is typically confined? And so, like in the previous slide, we have to increase the energy. And so we can do this by raising the temperature or by succumbing it to pressure. And so then we get this deconfined state of quarks and gluons that we call the Quark-Gluon plasma. And so we have two phases of QCD matter. So that means we have a phase diagram. And so in the same way that you're familiar with, for water, you have a phase diagram for water that's mediated by the electromagnetic force. QCD matter has a phase diagram mediated by the strong force. And so this is showing the phase diagram for QCD matter. The temperature as a function of baryon density, which you can think of as the pressure. And so you can see at low temperatures, we have the hadron state, but then at high temperatures, we have this Quark-Gluon plasma state. And you can see here that the temperature for this phase transition occurs is here, and this is like 4 trillion degrees Celsius. This is 250,000 times hotter than the center of the sun. And so this Quark-Gluon plasma state was a state of the early universe. So in microseconds after the Big Bang, we had a state of 3 quarks and gluons before they confined into hadrons. But of course, we can't go back in time. And so how can we study this Quark-Gluon plasma now? And so what we do to reach high enough temperatures is we use high energy particle accelerators. And so if I return back to this phase diagram, you can see that colliders like the Large Hadron Collider are reaching temperatures high enough to overcome that phase transition. Additionally, I mentioned that we could go to like higher pressure. So down here on the phase diagram, we actually think that in high pressure neutron stars or neutron star mergers that a deconfined state of matter is produced, which has been supposed to be studied using gravitational waves. Today, I'll focus on studying this QGP in this like high temperature regime. And so we do this high energy and nuclear physics at 2 different high energy particle colliders. So first at the relativistic heavy ion collider, which is at BNL, so it's on Long Island, which is across the Sound. And then we also do this at the Large Hadron Collider at CERN in Switzerland. So you may be more familiar with CERN, where you're doing like particle physics, but we also do nuclear physics, this kind of nuclear physics there as well. And so you may be familiar with this picture of the LHC, where around the collider you have different detectors, which represent different experiments and different collaborations. And this picture also exists at RIC. And so actually here at Yale, there are people doing this nuclear physics at STAR, at RIC, and also on ALICE at the LHC. And so in my career, I did my PhD on ATLAS, and then my postdoc I've been on ALICE. So the focus on this talk will be on measurements at the LHC with ATLAS and ALICE. So how do we actually produce this QGP in the lab? So we use heavy ions, and we smash these heavy ions together at very high energies. So we're reaching almost the speed of light. Because of that, they Lorentz contract, and then they smash together at like pancakes. And then we get this Quark-Gluon. We get a brief phase of this Quark-Gluon plasma, which quickly hadronizes or forms final state hadrons that we detect. And so taking a step back from this kind of this cartoon picture, we can look at how the heavy ion collision is evolving in space and in time. And so if you think of the lead-lead collision or the heavy ion collision happening at time 0, the Quark-Gluon plasma is formed around a few Fermi over C, which is about 10 to the minus 3 seconds, and then it quickly hadronized. So we essentially have it hadronized by about 10 Fermi over C. And then we get a bunch of final state particles in the detector. And so how do we detect these final state particles from the collision? And so like I showed in this picture of the collider, where you have many detectors around the collider, we have these large detectors to essentially study these collisions. And so I'm just going to focus on the examples that I've worked on, which is the ATLAS detector and the ALICE detector. These are massive detectors. Like ATLAS is about 6 stories large. But ATLAS is essentially optimized for high collision rates or high luminosity, so doing like discovery physics of particles. On the other hand, ALICE is optimized for heavy ion collisions, so doing like precise identification of particles and precise tracking. And so what do these heavy ion collisions actually look like in our detector? And so what I'm showing here is in the ALICE detector, what a standard proton-proton collision looks like, which is your particle physicist is what you're more familiar with, compared to what it looks like in a heavy ion collision. So you can see the detector is like lit up. So we're getting a bunch of final state particles in the detector from this QGP medium. And so in our experiments or in our measurements, we actually use the proton-proton collisions as essentially a control. And so So now we can produce this QGP medium, but what are its signatures or properties? And so one signature is that it has a low shear viscosity. And so what this means is that it's a nearly perfect fluid. It's actually the most perfect fluid ever measured. And because of this perfect fluidity, the soft or low momentum particles should collectively flow, and this can be characterized using hydrodynamics. On the other hand, this is a fluid, but at some scale, it's still these quarks and gluons, and so the medium is expected to have a high opacity. So it should be hard for something to move through it. So essentially hard for a colored object to move through it. And so we can study this by looking at energy loss of colored objects or QCD probes. And in my research, I use a particular QCD probe or QCD microscope called the JET. And so how do we produce this QCD microscope? So we can return back to the picture of the colliding ion, where in this collision, you have actually individual protons colliding. So you can zoom in and look at like the standard proton-proton collision. And in these protons, you have quarks. So these quarks will scatter with a high momentum transfer, which is called a hard scattering, and then produce quarks, alkaline quarks in the final state. And so, but like I mentioned earlier in the talk, these quarks cannot exist on their own. And so once these quarks are produced, they actually shower additional quarks and gluons, both in the initial final state. And this is called a parton shower. And then eventually the shower reaches a low enough energy scale that the partons can combine together to form hadrons, or they hadronize or hadronization. And so what we end up with is these final state hadrons in the detector. And so we group all of these final state hadrons together in a cone and call this a jet. And this serves as a proxy for this initial quark or gluon that we can't measure. And so jets are a very useful tool because they connect measured hadrons to unmeasurable partons. And so we have these jets, which are multi-scale dynamic objects with complex structure that contain QC. So while I was talking about using them to study the Quark-Gluon plasma, they're also a useful tool for studying this QCD in general. And so I'll come back to this later in my talk, but just a quick example, I talked about this running of the coupling constant. Actually, measurements of jets were used to constrain them. So, yeah. Okay, so we're turning back to this picture of using jets as a tool to study the QGP. And so these jets are actually formed early on in the collision, so before the medium is formed. And so because of that, they evolve through the entire QGP evolution, and therefore they can encode information about its properties as they propagate through it. And so when we think about these jets moving through the Quark-Gluon plasma, we talk about the phenomenon of jet quenching. And so what this is if you look at this picture of a jet in proton-proton collision, then imagine that these jets are now moving in the medium. And so the partons inside of the jet will strongly interact with the medium, and this results in both energy loss of the jet and a modification of the complex structure of the jet. And so this picture is a little bit more complicated than that, because we expect kind of different interactions with the medium at different scales. And so, for example, when the jet moves through the medium, the partons inside of the jet will emit a soft gluon when they interact, and because there's multiple partons, you can get multiple soft gluon emissions. And so this property essentially causes a softening and broadening of the jet, so the jets are widened in the medium. Additionally, we have the jet is moving through this fluid, right? So when it's moving through this fluid, the fluid can actually respond to the jet. So the fluid responds to the jet and actually causes a wake that can push soft particles back inside of the jet. Additionally, the jet pushing also matters. Another thing that matters is essentially the initial jet probe. So for example, we expect jet pushing to have a flavor dependence. So we expect the energy loss of gluons to be larger than the energy loss of quarks, and also the energy loss of heavy quarks to be less than the energy loss of lighter quarks. And this essentially comes from the color factors in UPCD. Also, jets look different in the vacuum, just essentially due to differences in the proton shower and hadronization. And so we can get different complexities for the jet. And so a more complex structured jet has more opportunities for interaction with the medium and could experience more energy loss. And then finally, we actually get that quark jets are narrow and have less structure than gluon jets. And so how do we actually measure these jets in the detector? So in this picture, we have the proton scattering, the partons that hadronize, and then they end up as either charged particle tracks in a tracking detector, or they can deposit energy in a calorimeter. And so if you remember from like a couple of slides back, I talked about the two different detectors. So Alice is optimized for precision tracking. So here you're measuring jets with tracks. And then Atlas is optimized for calorimetry. So here you're measuring jets with clusters. And so what we do is we've been grouped together. These tracks are clustered using a jet clustering algorithm to form our experimental jet. And then this experimental jet has a defined transverse momentum and a defined resolution parameter R, which is essentially the cone or the aperture at which we measure the jet. And so just to give you a picture of what these jets look like in a bit display. So this is showing a jet just in the proton-proton collision. This is from event display from CMS. And so this is essentially looking at energy deposits in the calorimeter. So think of this as like unraveling the calorimeter in space. And so what you see is these two high energy objects that are jets. The situation gets more complicated when we do this in heavy ion collisions. And so here we have this large background in heavy ion collisions. And so this is coming from essentially this underlying flowing medium that I talked about at the beginning of the slide. And so it looks a bit different than the proton-proton case. So you see like a clear jet here, but there's this large background underneath, and there may be jets hiding under the background that we need to find, because this background could be of the order of jet. And so this background contributes energy inside of the jet cone, and also upward fluctuations in this background can look like jets and be reconstructed as jets, and these are called shapes. And so one of the biggest challenges in doing these measurements is overcoming this issue of the background, because it can obscure the physics message and also restrict where we can measure jets. And so kind of underlying the measurements that I'm going to show today, they've all required innovative techniques to overcome this challenge. Okay, so now how do we actually measure jet quenching in an experiment? And so what I do is I construct jet observables to get at different aspects of jet quenching. And so first we can look at correlations of particles to get at the kind of the relative energy loss of jets. We can look at suppression of jet yield to look at the absolute energy loss of jets. And finally, I said the structure of the jet is modified, so we can look at this by using jet substructure tools. And so throughout my career, I've worked on measurements of all of these types of observables to try to get a better understanding of the Quark-Gluon plasma. And you'll see as I work through them that like increased sophistication of methods of time has allowed us to deepen our understanding of the QGP.
And so I'll start with talking about these correlations. Looking at these correlations in the jets is kind of the first most obvious way to measure jet quenching. So dijets are the most popular configuration from jets. And so if you look back at the picture in a proton-proton collision, you have two jets that are back-to-back in balance. Then they have to, in the heavy ion, in the PPP, they have to move to the medium. They can move through different paths. And so you can expect an imbalance because of the different path that they travel. And so one of the first measurements of this was done by STAR, where they weren't actually measuring jets yet. They were looking at correlations between particles. And so they essentially looked at the correlation of particles near the jet and away from the jet. And so if you look at this plot in the left, which is showing the near side, you can see the proton-proton is in black and the gold is in red. You can see that there's clearly a hadron here, but if you go to this away side, you see that in proton-proton collisions, you still see the peak, but in the gold collisions, the peak has disappeared. And so this was actually the first observation of jet quenching, which was done at Frick, and it was actually Mike Miller's PhD thesis here at Yale. This was done in 2003. So then the LHC turned on. And so when the LHC turned on, we could actually measure fully reconstructed jets. So not the hadrons anymore, the fully reconstructed jets. And so what I'm showing here is an event display from Atlas where you're expecting a dijet event. And so what you see is a clear jet on one side and no jet on the other side. So you're seeing this jet, the jet that was on the other side has lost energy. So I really like this event display because it's just a visual representation of jet quenching, which jet has lost energy. But when I started my PhD, I wanted to essentially quantitatively measure this. And so I use an observable called XJ, where we're essentially comparing the higher momentum jet to the lower momentum jet in the event to look at this imbalance. And so this is what the result looks like. So this is looking at this XJ variable in lead-lead collisions in red compared to PP collisions in blue. So if you focus first on the PP case, you see it's got a clear peak around XJ equals 1, which makes sense. That would be balanced. But if you look at the heavy ion case, you see a peak at around XJ equals 5. So we're seeing a striking asymmetry and imbalance in the medium. And so here we had a more quantitative picture, clear evidence that different jets use different amounts of energy in the. And so now I'll move on to measurements of jet suppression. And so here, before kind of going into the details of the measurement, it's useful to look at a picture of what a jet PT spectra looks like. So this is just showing a measurement of a jet PT spectra in proton-proton collisions. And the thing to notice is that this is a log scale. So this spectrum is like very steeply falling. So jets at very high momentum are a lot rarer than jets at low momentum. And so we can get at this picture of energy loss in the spectrum with this picture. So think of the blue line as being like before energy loss, and then it experiences some energy loss in the purple, and then the red line is after energy loss. So then at a fixed value of momentum, you get a suppression of the yield. And so in our measurements, we quantify this suppression by using this variable RAA, which is essentially taking the ratio of the yield in lead-lead to the yield in PP scaled to account for the differences in the geometry. And this is essentially just the ratio of this red to blue line. And so if this is less than 1, we're seeing suppression. And so another measurement that I did while I was on Atlas was essentially taking advantage of the Atlas high collision rate and measuring jet suppression over a very large range of momentum. So this is showing the RAA as a function of PT going from 100 to 1 PV, so an order of magnitude. And so what's interesting is that this this suppression actually persisted at very high PT. We thought that maybe a jet moving through the medium at high PT might just like punch through and not interact, but it did. So we're seeing jet punching even at high PT. And so this jet suppression has been measured over a very large range of momentum, kind of taking advantage of different capabilities of different detectors in our field. So the high PT regime that I measured on Atlas, also Alice measured this in a more intermediate PT range, and STAR at Rift has measured this at a lower PT range. So now it's from 10 to 1 TeV, so over 2 orders of magnitude, we're seeing this energy loss. And so these measurements have been compared to different models, to different jet quenching models. And essentially the picture is that the models seem to describe the data fairly well, but the question is what do not do match? And so when I started my postdoc at Yale, I started working on a project with actually graduate student who's here in the room at trying to get at this question of how do we disentangle the different effects that I talked about earlier when thinking about jet suppression. And so the way that we decided to do this was increasing the cone or the aperture of which you measure the jet. And so as you change the cone, the impact of these effects will vary. So for example, for the medium response, the RA should increase. For the momentum broadening, you may get because of this broadening, you may get a recovery of the energy outside the cone. So the RA should increase. But then also we had these kind of different jet probes of populations where wider jets have more structure or they might have more gluons and the RA could decrease. And so we quantified this effect by looking at the ratio of jet suppression at large R to a smaller r. And so if the RA increased, this should go up. And if the RA decreased, this should go down. And so the idea was to measure this R dependence of jet suppression to try to disentangle these effects. And so in doing this measurement, the heavy ion background poses a problem because as you open up this radius, the background has a larger impact. And so the standard method for removing the background is we use a pedestal subtraction, where we just move the average energy inside the jet. And so this is showing kind of the resolutions, like our ability to measure jets as a function of the jet radius, and like below this is where we can measure. And so with this method, you can see that for the larger R, we can't do measurement. So what we did is we applied a new machine learning method in this environment, where here we took advantage of the complexity of the jet to just better distinguish the signal from the background. And when we did this, the resolution substantially improved. I just lost the color that was inside. And we're able to measure out to larger dot. Okay. So yeah, so this is showing the results of the measurement. So this is the double ratio as a function of PT. And the thing to notice is that we see it less than 1. So we're seeing the larger, wider jets being more suppressed, or we're seeing a narrowing effect in the Quark-Gluon plasma. What's also cool here is that we're comparing the models, and if you remember before, now this observable actually has a better discrimination power for models. And so, like I said, the decreasing feature could come from different jet populations. And so we actually with the summer student this summer, Mary from Colby College, we investigated this. So she implemented essentially only the flavor dependent component of the energy loss. And this is the results. So the results of what she measured is in the blue. And so you can see just having this simple flavor dependence actually starts to describe the data and gets this suppression effect. Okay, so moving on to measurements of looking at the modification of the structure of the jet. So when I was starting my postdoc here, I was interested in essentially going deeper, so going past just like energy loss and trying to understand the actual modification of the details of the jet. And so we can return back to this picture of the evolving medium. And so the idea is that the medium is evolving in space and time, but also the jet is evolving in space and time. And so we can essentially use the kind of complex dynamics of the jet with the parton and the hadron structure to access a more detailed picture of the space-time structure of the GPU. And so when I was starting my postdoc, there's actually a lot of work going on in like the high energy physics community, both on the theory and the experimental side. They were designing jet substructure tools to study both fundamental QCD and also to do like particle physics searches. And so one particular tool that they were using was they were measuring subjets within a jet. And so here, the subjet within a jet serves as a proxy for the proton splittings inside the jet. And so this observable was nice because it's motivated with theory and practical and conservative PCD. And so I asked the question, can these jet substructure tools be used and applied in the heavy ion environments to study the modification of PGP? And so it was nice that I was on ALEKS because ALEKS is very precise tracking. So we were able to take advantage of this precise tracking to kind of get this detailed picture. And it was also cool because in this kind of, at this time, like we had a merging of like two jet communities. So the community studying just QCD became interested in PGP and vice versa. And I was actually one of the people that became interested in studying just QCD for the sake of QCD. And so one tool one jet substructure tool that I I've used is the loon plane. So what the loon plane does is it provides a visual picture of the patterns inside of jet. And so it provides like a phase space of these splittings inside of the jet. And so if you look at this picture over here, so I'm showing two subjects inside a jet with momentums PT1 and PT2. And then in this diagram, you can have the KT or the relative momentum transfer or the momentum scale of the splitting. And you can also have the delta R or the distance between the subjects or the angular scale of the splitting. You can also have lines of diagonal lines are lines of constant Z, which is the shared momentum fraction. And then additionally, also going in this direction, you have formation time. So essentially how long until the splitting occurs. So you have this time also in this plane. And so in my research, I have used this loon plane both as a tool to study in the vacuum to essentially map the phase space of PCD. And also I've used it in the medium to try to study the space-time structure of the QGP. And so I'll start with a measurement looking at it in the vacuum. And so here, like I said, this loon plane can explore the phase space of PCD. And so what's nice is that if you remember this picture of the jet evolution, the different components of the jet evolution have like a unique spot in the loon plane. And so, for example, the parton shower is at like harder, wider splittings. The hadronization effects are at like softer collinear splittings, etc. And so also in this plane, we have the KT or the momentum scale. And so we can look at a KT around lambda PCD and access the confinement transition from partons to hadrons. And then additionally, we have the shape of this plane is because of this is actually sculpted by the running of the coupling. And so now I'm showing a measurement of the loon plane with ALEKS proton-proton data. And so this is the same picture, but now in data. And so the thing to notice is you do start to see these visual features emerge. And so and the idea is that you make projections in this phase space and make comparisons to different Monte Carlo generators, like if you're a particle physics, like 50, etc. And making these comparisons are extremely important for informing these generators in both particle and nuclear physics. And so before I move on to talk about this in the heavy ion environment, I wanted to highlight a particular cool application of the loon plane. So the loon plane was actually used to uniquely access the PCB dead-cone effect. And so what this is when you have a heavy quark, you actually expect a suppression of the emissions in near the quark. And so you get like an empty cone or a dead cone around the quark. And so you don't expect to see as large of a dead cone for the light bursts. And so this measurement that was done by Alice, what was done was actually measuring the loon plane for charm type jets and comparing it to inclusive jets. And so this plot is showing the ratio. And so the thing to notice is that this is the angular scale. So we're seeing a suppression of the charm jets at small angles, and this is consistent with this dead cone effect. And so this was the first direct observation of the dead cone effect on the nature. So now we'll move on to how this loon plane can be used as a tool to study the QTP. And so, like I said, it can be used to study the space-time structure of the QTP. So now we have this medium in the plane. And so the idea is that these splittings can happen at different times. And so we expect wider splittings to form earlier and narrower splittings to form later. And so because of the QTP, the wider jets could experience more of the medium and narrow jets and experience more quenching. On top of this, we can ask the question, does the medium resolve the structure of the jet? And so here, we're getting at a fundamental property of the Quark-Gluon plasma, the resolving power of the QTP. So to what degree can the medium resolve the structure inside of a jet? So I like to think of an analogy here. You think of a telescope. So you have like two stars at some distance. So your telescope, you have some resolution. You can either resolve the two stars or you cannot. And so we have the same picture in the Quark-Gluon plasma. The Quark-Gluon plasma has this resolution length. And so essentially, if it's large, then you can't resolve the structure inside of the jet and you get coherence, or you get the jet modified as a whole object. If the resolution length is smaller, then you can get, then the medium can actually resolve the structure or the color charges, and we can get decoherence. And so in this picture, the medium can interact with both of the color charges, and so you can imagine that you can get sometimes like wider jets being resolved and narrow jets not being resolved. And so you also have in the loon plane a region of resolved and unresolved splittings. And then finally, we can get essentially gluon radiation, so a medium-induced splitting, which also has a spot in the plane. And so this loon plane is a tool that now has this two-dimensional picture of different jet medium interactions, and we can use this to separate out some of these effects. But of course, when we're doing these measurements in heavy ion, I talked about the problem of the background. So we have soft particles from the background and also from things like the medium response that can obscure the physics message. And so I applied another tool that was inherited from the tech community, grooming, to essentially suppress the background and remove the softer components to focus on the hard splittings inside the jet. And so when you apply the soft graph, you can measure different observables to get at different medium effects. So for example, you can measure the shear moment refraction CG, which gets at how symmetric or asymmetric the jet is, and you can maybe access in medium splitting. We can also look at the angular scale, which looks at how wide or narrow the jet is, and we could maybe probe the resolution. And so I'll focus on the RG case where we saw some interesting results. And so here we're asking the question, does the medium resolve the structure of the jet? And so this is the measurement that I did in Alice. So what I'm showing here in the blue is the proton-proton data, and then the lead is lead-lead data. And then the bottom panel is the ratio of the lead-lead to the PP. And so what you can see is there's a significant modification as a function of the angle, where we're seeing a suppression of the larger intersplittings, or a narrowing of the jets begin. And so this narrowing picture is very persistent. So I already talked about this measurement that I did with Hannah, where we saw this by looking at jet suppression, but also many different substructure measurements from the LHC have shown this narrowing picture. So what causes this narrowing effect? So in this measurement, I compared to some different jet quenching models, and I'll focus on two. So the first is a model that looks at the role of this color coherence, of this resolving of the medium. And so what is seen is that a model that includes some decoherence effects can reproduce this narrowing effect. But on the other hand, another model looks at coherence, but changing the Quark-Gluon fashion, so looking at the difference between Quark and Gluon energy loss, this also can reproduce this narrowing feature. So this measurement provided a quantitative comparison to models where both decoherence and flavor effects predict the narrowing. And so just to think about this a little bit deeper, where does this narrowing really come from? So when we're measuring these jets in the QGP, we're actually measuring a modified jet and comparing to unmodified jets in QGP. So essentially, we're always measuring less quenched jets that have survived the Quark-Gluon plasma, and so we end up with a selection bias. So in this narrowing picture, what happens is we end up with the wider jets are more suppressed, so we're left with less quenched narrower jets. And so, okay, so now to summarize, what have we learned so far? So I've showed you that jets provide a multi-scale probe of the QGP medium and QCD in general. I showed that precision measurements of energy loss in the QGP can provide a quantitative picture of jet quenching. I showed that we can use carefully crafted jet substructure observables to reveal patterns inside of the jet and isolate fundamental QCD effects and also QGP effects. We're beginning to see a space-time picture of the QGP, but it's challenging to isolate these effects and actually extract QGP properties. For example, we saw this narrowing, but we see that it's probably coming from a selection bias that makes it harder to interpret. And so, and finally, I showed that we can use novel background subtraction techniques like this machine learning method to access new regions of phase space and revealing the physics. So now looking towards the future, so three things that I think would be good to address when looking to the future for jets and heavy ions. So first is better isolating jet medium interactions, but fully map the space-time picture with QGP. So here it will be helpful to have more statistics, so we can do more differential measurements, and also to have more of a handle on the jet probe. Additionally, we always want to access new regions of phase space to look for new physics. So this is improving background statistics and trying to overcome the selection bias to access these quenched jets. And then finally, designing new theoretical motivated substructure tools to try to continue to try to better isolate these effects, and this also can improve comparison to models. And so we're sitting at an ideal time right now. Most of the data that I showed, or all the data that I showed today, were from Run 1 and Run 2 at LHC. We just underwent a long shutdown where Alice received substantial detector and software upgrades. And so, for example, one of the upgrades was new tracking with gas electron multiplier, or GEM technology, which will significantly reduce the readout rate of the TPCs. And this was our technology that's actually developed here at Yale by Dick Nicklar. Additionally, we have like software improvements. So for continuous readout of data, so we can store every collision. And finally, improved inter-tracking system for precise measurement of heavy flavor. And so what does this mean for jets? So we'll have about 100 times more jets in this data. So a lot more statistics for measuring jets. We can look at precision. We'll be able to do precision measurements of charm tag jets and also as sets of beauty tag jets. And so we're sitting at an excellent opportunity to measure jets and heavy flavor jets in upcoming proton-proton and heavy ion data. And so now coming back to this question of towards the future. So With Alex, we can get more statistics for more differential measurements and also to vary the approach. And so just some examples of what this will look like. So with respect to the space-time picture of the CGP, we can think of a multidimensional picture of the in the balloon plane and look, for example, at an extra axis, which can look at the mass dependence of energy loss and ask what happens to the dead cone in the medium. These will all require requiring the ability to access new region of phase space. So continuing to work on new background techniques and overcoming the selection bias. And I think we can use machine learning techniques, some of the ones that were developed here at Yale. And then finally, with respect to new observables, I'm really excited about one observable, which is energy correlators, which is actually theoretically proposed by people here at Yale, Ian, Evan, and Bianca. And so this observable is more connected to the fundamental theory and should provide a better separation of scale. So here we can hope to study confinement, the dead cone effect, and the end effects of the future. So I promised that I would return back to this picture of this complex structure inside of the proton. And so essentially my research has been focused on like the deconfined state of QCD matter. So now with the future electron ion collider upcoming, we're returning back to the fundamentals to ask how are these protons arranged inside of these atoms. And so the next QCD frontier will be at the electron ion collider. So we'll have an electron beam colliding with an ion beam. This is going to be built at the relativistic and ion collider in Brookhaven. It will be the first polarized electron proton collider and the first electron ion collider. While this is in the future, detector development, big project detector developments are already underway. Recently the detector design for the active detector was approved, and this is going to be called EPIC. And so I wanted to just briefly say what the physics programs are for the EIC. So we'll be asking questions like, how does the proton get its mass? What accounts for the proton spin? Can we access a new state of matter by looking for gluon saturation? Can we continue studying the physics of confinement in a cleaner environment from jets? And finally, can we look at Quark-Gluon energy loss in a full QCD matter? And so, in answering these physics questions, jets will be a crucial tool. And so, for example, jets are these multi-scale objects, so they can access the momentum scale ranges to study this gluon saturation. We can also look at jet energy loss in the cold nuclear matter in the same way we look in the hot nuclear matter. And finally, I think we can use jet substructure as a tool to 3D image the nucleon in the same way that it was used to study the QGP. And so I'll finish by showing a picture of the first lead collisions at the LHC with the new data that this was from back in November, and say that this makes me really excited for the future. And yeah, so thank you, and I'm happy to take some questions.
Okay, we have that wonderful talk. We have time for questions. So, are there questions online?
I don't see any questions in the chat, but there are several people. So if you have if you're in the outside presuming you have a question, go ahead and raise your hand and we can give you the floor.
While that, Bob?
So I have two unrelated questions. If in the beginning of your talk you said that the heavy or the hard collision happened before the QGP was formed, how do we know that?
I think we know that these are colliding partons inside of the ion. So this is like even a proton-proton collision, the first thing that's happening is these hard scattered collisions. So it's essentially like the first thing that happens is the colliding nuclei or the colliding protons inside of the nuclei. So it has to happen first.
And towards the end of your talk, you mentioned new physics 2 or 3 times. Tell us what you mean by new physics. Do you mean what I mean by new physics?
No, I don't mean like discovering a particle. No, that's not what I mean. I meant like, for example, this measurement that I worked on with Hannah. when we like open the cone of the jet, most people expected that it would go up, that we would recover the energy, but we saw like the opposite effect and we saw it go down. So I mean that like, and like this was, and we're in this measurement, we were really accessing a new region of space that would not have been able to have been measured without this technique. So what I mean by that is that like new techniques to access the region of free space may reveal unexpected physics that will like tell us something new about the, that's what
I guess I had a somewhat technical question about this really nice measurement, looking at these wired cone angles. I think it was like slide 28.
Okay.
So, I mean, I understand why wired cones are harder to see because you have these backgrounds, and that seems pretty hard to beat. So do you have an idea of what the machine learning algorithm picks up on? Like, are there features that allow it to see those?
Yeah, no, that's a great question. So essentially like a jet that looks like a signal jet should have like a hard core. And a background jet is not going to have so much of a hard core. So we think that the machine learning is picking up on differences in like the features of that hard core to like get a better idea of what's a jet and what's not a jet. Because in the standard method, we're only using the energy to do this.
So I guess the follow-up then is, are there classical methods then using that kind of harder core model instead of just that flat background suppression that reproduce the kind of signal the backgrounds you see? Like for us, often we can discover things with machine learning, but it makes us feel better when we can explain it with a classical algorithm.
So that's a great question. So the algorithms that for example, like the algorithms that maybe would look more at like subtracting the background on like the structure of the jet have been more developed for calorimeter jets. While we thought it would be a good idea to try something like that, there wasn't really an algorithm out there to do it. And even with these algorithms in the calorimeter jets, like Atlas does this, for example, they can't measure this region. So with the tools we have out there today, right now, we were able to access a new region that the other methods have not been able to access. But maybe in the future there might be some new methods that this could do it, yeah, like for sure. But we see this feature not just here, like in this, we see this narrowing is what we saw. We see it in a lot of other places as well. So that also gives us sense that that it has the right picture.
So you described the plasma as this ideal fluid. I sort of wonder if there's any reason why collective excitations of this fluid might alter your jets. Maybe that's some global thing, like some collective oscillation or something like turbulence that produces.
So you mean like how, so yeah, so like I guess like when we think about the jet we think about you could have interplays between the jet and the medium that affect the evolution of the jet in the QGP. Yes, for sure. And like the one effect that I even talked about was actually like an interaction with the medium where it like the softer stuff where it like produced this weight that like pushed particles back inside the jet. So that is like the fluid like doing something to the jet. So yes, yeah.
Can I follow up?
Sure, yeah.
Like, is there a sort of difference between different kinds of excitation? So you mentioned the weight. Like, are there any thoughts about that weight producing something like vortices or something in here that like really alter the jets in a way that's a nice signal for you? Or?
So not necessarily with respect to jets. There are like studies of that in the like soft features of the QGP, but not its interplay with jets. No.
Any other questions? John.
Yeah, I'm motivated by Paul's question. I have to ask this one. This isn't a plug or anything. I was old enough to have talked to Bjorkane a few times. And Bjorkane 30 years ago, actually 40 years ago, he had a seminal paper on parton propagation through the Quark-Gluon plasma. And in my discussions with him 25 years ago, you know, he always said that the plasma is a plasma of dipole. And so my question to you is, you know, can you tell whether it's diquarks or not?
What do you mean by diquarks? Like
to bar, whatever two quarks you want.
Oh, so you mean like when we measure
That's
the,
what we thought of.
oh, you mean like when we measure the final state particle, can we like look at, can we like measure them and like try to identify something like those states? Yes, we can measure things like Quark-Gluon and things like that by looking at. these-
Right,
these-
but I'm talking about the microscopic structure. The QGP, as it's expanding, and you have partons, and this was motivated by a discussion I had. You know, can you, using your techniques, determine the structure, microscopic structure, or whether it's diquarks or not?
So I think maybe whether it's diquarks or not, I would not claim to be able to say that in the near future, but I think this idea that you're suggesting of like using the jet to get at the more microscopic structure of the QGP. For example, I didn't talk about things like the jet can like deflect off of a quasi-particle inside the medium. So I think we can use jets as a tool to understand this really microscopic structure, which is like the idea that like, even though we have this fluid, it's made up of these quarks and gluons, and they may not be like fully free. They may be like in more like smaller confined space. I think so.
Do one of us check anyone online? A question?
I don't see it.
No? Okay. No, any other last questions? Not, let's thank Laura again for a wonderful.